Alright, welcome back to the functional programming sections, people. I'm already proud of you for making it this far. In this video, we're going to make the transition from object-oriented to functional programming by discussing what a function actually is. Alright, so in the IDE, I'm going to create a new package just for this section. So on the lectures package, I'm going to create a new package. And let's just call this part 3, functional programming. So here is where we will store our applications for this section. For this particular lecture, let's go ahead and create a new Scala class, and let's call this what's a function. And make this an object, of course, and extends app. Good. Now, the whole purpose of the functional programming section is to use and work with functions as first-class elements. What that means is that we want to work with functions like we would with plain values. That's the dream. The problem is that we come from an object-oriented world. And when you come from an object-oriented world, basically everything is an object. That means it's an instance of some kind of class. This is how the JVM was originally designed for Java, for instances of classes and nothing else. So the only way that you could simulate functional programming was to use classes and instances of those classes. So in Java, and also in object-oriented Scala, we would write a class called something like an action, with a method called, say, execute, which, for example, takes an int and returns a string or something else, right? So we would write something like this. We would write classes and methods. And the way that you would use these things as quote-unquote functions, although I cringe at the term, would be to instantiate this class either anonymously or non-anonymously. So if you remember what we did with my list, if we go to my predicate here, right, at the end, we're using predicates and transformers like quote-unquote functions, but they're actually instances of these classes with on-the-spot override method definitions. So this is how you would work with these functions, so to speak. You would actually work with these function simulations. All right. At most, what you would do would be to genericize and abstract away most of the boilerplate so that you could use generic types. So our action here would be some kind of abstract type, like a trait, and action would take parameters, type parameters. And we would say that this action execute takes an element of type A and returns an element of type B. So this is at most what an object-oriented language would be able to do. Again, this is how the JVM is naturally constructed. So Scala had to resort to some clever tricks to make it look like a truly functional language. So a better design would be to just rename this to, let's call my function, and instead of this execute, rename this to apply, which by now you know that has a special meaning in Scala. So if we have a little my function, let's say new super function, or let's say doubler, which is a new my function. Let's say this doubles an int. So this is my function from int to int, and the override def apply takes an int, element of type int, and returns an int, and let's just say it returns element times 2. This is an instance of this little function-like class. But the advantage of Scala as opposed to Java is that we can actually call doubler of 2 like it were a function. So doubler acts like a function. I'm going to switch to presentation mode so you can see the output. So if I right-click and run this, doubler actually calls the apply method, and this is going to print the number 4 to the console. All right. So for now, doubler, which is an instance of a function-like class, can be called like a function. Now, the interesting thing is that Scala supports these function types out of the box, and the function types are function 1 or function 2 or function 3 up to function 22, but for function with one parameter and one result, this is function 1 with a and b. So this is a function type which is by default supported in Scala. So if, for example, I create a val, let's call this a string to int converter. All right, and this will be a new function 1, and look at the IDE. So the IDE already suggests the function types for me. So new function 1 with, say, string and int, and they work in the same way. So override def apply with string, which is of type string and returns an int, and then just say the implementation is string to int. So just as a simple implementation. And now I can actually call this string to int converter, and let's just say I call it, quote unquote call it, with the string, say 3 plus 4. So this thing returns an int plus 4, I should get a 7 at the console. All right. Now, by default, Scala supports these function types up to 22 parameters. So, for example, if I have a function that takes 2 ints and returns an int, let's say adder, that would be a new function 2 with int, int, int. So these are the parameter types, and this is the result type. And the override def apply takes 2 parameters, say a and b, both int, and the return type is int. And let's just say it returns a plus b for a simple implementation. Okay, so this is a proper function. Now, the type of adder is, if I hover, it's this guy, int, int, arrow, int, which is syntactic sugar for function 2. So if I say adder is a function 2 with int, 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 this is the correct type, right? But a syntactic sugar for this type is int, int, in parentheses. These signify the parameters, and arrow, int. This is a syntactic sugar for function 2. So this is getting closer to functional programming. So we have function types. For example, function 2 with 2 type parameters and with a result type parameter, we write this as AB arrow R. We're going to start using these a lot more as we go through the functional programming section. But the elephant in the room in this lecture is the major takeaway, which is, and I'm writing this in all caps, all Scala functions are objects or instances of classes deriving from function 1, function 2, etc. So we're laying the groundwork here for Scala as a functional programming language based on the Java virtual machine, which was never originally designed with functional programming in mind. The JVM was designed with object orientation in mind. And as we'll see throughout this section, through a series of syntactic features, we'll get to Scala as a truly functional language. Alright, so let's practice what we've learned. I want you to go through a series of very simple exercises. First, I want you to define a function which takes 2 strings and concatenates them. So this is dead simple. I just want you to use this function type. Alright. Second, I want you to go ahead and go to the myList implementation and transform the myPredicate and myTransformer into function types and see what you find. Third, I want you to go ahead and define a function which takes an argument an int and returns another function which takes an int and returns an int. First of all, I want you to, for this exercise, define what's the type of the function, of this function, and how do you do it? How to actually implement this special function, so to speak. So, as always, pause the video and think through these exercises, and in a couple of seconds, I'll jump in with solutions. Alright, so I hope you did it. Let's take them in turn. So, a function which takes two strings and concatenates them. This is dead simple. So let's call this concatenator, which is of type string, string, arrow, string. Alright, and the value for that is going to be a new function 2 with string, 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 and the implementation of the apply method is going to be override def apply. This takes two strings a and b, for example, all right, and returns a string, and it just concatenates them together. Of course, if I name the parameters differently. All right, so this is the concatenator, and if I print concatenator applied with hello and Scala, then I should receive the string hello Scala at the console, which is exactly what we expected. Now, for the myPredicate and myTransformer, let's go back to myList. So switching, let's go and investigate how these guys look like. So myPredicate and myTransformer are basically function types. If you take a closer look, so myPredicate is basically a function type from T to Boolean, and myTransformer is a function type from A to B. Right. Now, the revelation that I wanted you to reach was that the predicate and transformer types that we wrote in the object-oriented section don't make sense here anymore because we already have function types. So we can safely delete them altogether, and a bunch of things will now not compile, but we can fix them. And here, we can fix the myList abstract class by changing the transformer to a function 1 or to an A arrow B type. And the transformer here is going to be an A arrow myList of B type. And the predicate, as we discussed, is an A arrow Boolean type. Okay, and suddenly all the things now seem more functional programming like. So let's change the function signatures throughout the code. So myTransformer is a nothing to B. All right, transformer here is a nothing arrow myList of B. Predicate is of type nothing to Boolean. Below we have filter with myPredicate, which is of type arrow Boolean. Okay, now predicate.test doesn't really make sense anymore. So we can either call predicate.apply, which would make sense, or simply predicate, because we can now call it like a function. Again, below, transformer is an A arrow B type. And the transform method, of course, does not exist. We can call apply, or we can simply call transformer. All right. And on flat map, transformer of A to myList of B is just A arrow myList of B. So instead of transform, we can simply leave the apply method. Okay, and now the myTransformer, myPredicate, myTransformer don't really make sense, and we can replace them with function 1. Okay, and predicate is a new function 1 from int to boolean. All right, and transformer here is a function 1 from int to my list. And these methods are not called transform and test, but they are simply called apply. Okay, so we've suddenly turned my list into a more functional collection because it now uses functions as first-class values, especially when it comes to map, flatmap, and filter. These in particular are called higher order functions. Higher order functions either receive functions as parameters or return other functions as a result. Higher order functions are a critical concept to functional programming because it now uses functions as first-class values, especially when it comes to map, flatmap, and filter. These in particular are called higher order functions. Higher order functions either receive functions as parameters or return other functions as a result. Higher order functions are a critical concept to functional programming. So that was the exercise number 2. Let's switch back to what's a function and actually go to exercise number 3, which is a special kind of function which returns another function as a result. This is also a higher order function. So first of all, we need to decide what type this function is going to take. Well, the type is going to be function 1 because first it takes an int as a parameter, so this is the only parameter that this function will receive, so function 1, and the parameter is going to be int, and the return type is another function which takes an int and returns an int. So the return type is going to be function 1 of int and int. So this is going to be the final type of our special function. Let's use it. So val, let's call this special function, which is of type this guy. I'm going to copy it and paste it. So it's going to be a new function 1 of this type, and the override def apply takes an int, let's say x, and returns function 1 with int and int. So because it returns a function 1 with int and int, it will return a new function 1 with int and int. So it will have to return an instance of function 1, right? Okay. And the override def apply here will take another value y, which is an int, and returns an int. Okay, now we're free to supply an implementation here because I didn't really give it to you in the exercise. So let's just say that this just adds the two numbers, x plus y. Okay, so because x is defined in the upper function over here, x is visible inside the function implementation, which starts here. So x is also visible inside the result value. Let's rename this special function. Let's call this super adder because it's more suggestive of its implementation. All right, and let's create a little val adder. Let's call this adder 3. That's because I'm going to call super adder with parameter 3. Now adder 3 here is a new function. So the type of adder 3 is int arrow int, which is a function 1 from int to int. Now if I print line adder 3 with parameter 4, for example, then this will return 7 because the implementation of adder 3 is this guy, which adds x, which in this case is 3, passed to super adder before, and y, which is the actual parameter. So if I right-click and run, I'm going to see the value 7 here in the console. In the same fashion, I can actually write print line Superaddr applied with parameter 3 and then applied with parameter 4. Notice how weird this is. So superaddr applied with 3 returns a function 1, and then I can call that with parameter 4. So if I run this guy, I'm also going to see the value 7. This special function, so to speak, is called a curried function. In the same fashion, I can actually write println superaddr applied with parameter 3 and then applied with parameter 4. Notice how weird this is. So superaddr applied with 3 returns a function 1, and then I can call that with parameter 4. So if I run this guy, I'm also going to see the value 7. This special function, so to speak, is called a curried function. Curried functions have the property that they can be called with multiple parameter lists just by their mere definition. So a curried function actually receives some kind of parameter and returns another function which receives parameters. So basically superaddr can be called with multiple parameter lists to get to the final result. We are going to talk about higher order functions and curried functions in the next videos, but I wanted you to get a taste of what a curried function looks like. Alright, so let's recap. Our main motivation when starting the functional programming section was that we wanted to use functions as first-class programming elements. That is, we want to be able to pass functions as parameters or return functions as results. So we basically want to be able to work with functions like we are able to work with any other kind of value. But the problem is that Scala works on top of the Java virtual machine, which was never designed for functional programming in the first place. It was designed for Java, for which the first-class programming elements are instances of classes. Now, the only solution that would work for a functional programming language is to turn all Scala functions into instances of special kind of function-like types. And in Scala, we have function traits of up to 22 parameters. And a function trait looks like this. Ignore the variance modifiers for now. We also have syntactic sugar for function types. For example, if we have a function 2 which receives 2 parameters int and string and the return type is an int, this function 2 type has the sugar int string error int, and we're going to use these sugars from now on. Alright, so quite a promising start in this journey towards a truly functional language. I'm Daniel. Let's continue together in the next video.